welcome to this session of quantitative analysis, KASNEB. So this is a series of revision sessions organized by Datalytics, and I'll move straight away to the question of today so that we see how to answer a few questions of choice. So the paper that we are interested in is this, the one projected. So it's I could do that here. Yeah, that's better. So the paper is KASNEB, as we can see. It's yeah, it's KASNEB, as we can see, and CPA Part II Section 4, CIFA Part II Section 4, CCP Part II Section 4. The paper is referred to as quantitative analysis, and the paper was taken on Friday, 27th November of 2015. Time allowed is 3 hours. And today, my question of choice is that on profit maximization. So that should be question 2. So in question 2, we are asked to explain how differential calculus could be used. So let me just pick a highlighter. I want to pick a highlighter, just a moment. Let me pick a highlighter so that we get to know and see how we are moving. Yes, let me pick this. So the question I'm concerned with is this one. Question 1, part A. Explain how differential calculus could be used in solving optimization problems. That's 2 marks. But first, before I get there, I needed to have set up the environment where I want to do the rest of the session. So I'll grab Microsoft Whiteboard. And probably what I need is that's not what I need, but it's okay. I'll just get a new one. So closing this should mean, okay, let me just get started afresh. So there it is. So I need a new whiteboard. That's what I'll go for. That's a new whiteboard. And I think I should start with blank, like that, because now that's what I need. And probably again there's something I need to change. I need some change on the background, like that. That's better for me. So yeah, that's better for me. And yeah, what else do I need? I needed to have, yeah, I've just called it untitled whiteboard. But then first, let me ensure that I'm organized by having to subdivide the page on which I want to work on. And so I'll imagine that this should be the center. And so I want to yeah, let me pick this. Let me pick that. It will be there. It's okay. So yes, that's that. So I've actually marked an area where yeah, I think that will now work better. So I've marked an area where I'll be working, and just before I get there, what we needed to show is that the use of differential calculus, use of differential calculus in optimization. So we should know that in optimization, we want to maximize or minimize a function. Like we know that in economics, we deal with two major questions, that of having to maximize revenue or minimize cost. So either way, we employ the services of calculus to find the minimum or the maximum point, what we refer to as the optima. So in this question, what we have is, for instance, you may be having an equation y is equal to f of x. Now, in this case, what we have is that y is the independent and then f of x is the function. So we would want a situation, for instance, this y may represent the price and x may represent the quantity, price and quantity. So in this case, one may be interested in the quantity that say would maximize profit, something like that, would minimize cost, or something like that, knowing that profit is basically the difference between profit. Let me say there are things that we'll be referring to more often, so there's need for me just to set the record straight. So profit, I'll give it as that. Profit generally is given by the difference between revenue minus cost at the point of that's at the point of those units of output. So that's how we'll be defining our profit. So it means that what it means is that we need to define our revenue function to talk about profit. And we also need to define a cost function to talk about profit. In which case, the difference between revenue function and the cost function will be what we define, what we refer to as the profit in this case. So next thing is that what I mean to show is that if by referring to this function here, that is y is equal to f of x, which is a function that would be defined, then if we went ahead to get, say, we may be interested in getting dy dx, in which case that will give me f prime of x. Yes. So derivative of this function here, derivative of that function now gives me, it refers to that as that. Now, if I would want to find the second derivative, if what I'm interested in is in finding the second derivative, then I would refer to it as, so in which case now I would then differentiate this. I would then now differentiate this, in which case I'll now be referring to it as f double prime, to mean that I've differentiated twice. That function I've differentiated twice. Now, every other time in this case, this derivative, we need to equate it to 0, because at the turning point of the curves, like here, this we equate to 0, this again we equate to 0. The reason we equate to 0 is that at the turning points, where the curves are turning, like, let me just sketch. I should just sketch so that we see. Let me see. Just want to sketch so that we see what I'm talking about. So here I come here, and now I'll bring my ruler here. And in this case, what do I use? Let me use this. So I bring it here. Now I'm trying to draw I'm trying to draw the two so that it's clear. This is just an explanation for the purposes of benefiting the student. Otherwise, as you can see, we were not supposed to actually get there. So like here is 0. Let me reduce the thickness. That's so thick. Reduce the thickness. Yeah, that's better. So we would calibrate it as, okay, before even thinking of calibration, let me just say this is the quantity, this is the X, and let me call this, actually this is the price. That's the price. So what we are saying is that if the function yf of x represented the flow, because if we are talking about price and quantity, then we are likely to be referring to two curves, that of supply or demand. But we know in market dynamics, it may not be as straight as we may wish, like a situation where it's say that now we have, it's rare that we end up with a it's rare that we end up with a supply curve which is of, just a moment, let me pick the pen. Yes, it's rare to pick. Now it's rare to find, that's so thick, I didn't want it to be that thick, so let me remove, just a moment, let me just remove that. I pick this. Okay, whatever it is, let it stay. So it's rare that we have a demand, a supply curve that is of this shape. Rarely will you find this in real life. Rarely will you find this in real life, where this is a supply curve. Of course, we know that a supply curve should behave like this, where as prices increase, output is also, will also increase. But we are saying that in a this situation, if f of x here represented, say, the supply curve, then we would be expecting a curve that deviates from the straight line that I'm seeing. One where market dynamics will allow supply to increase with price, quantity supplied to increase with price. But there are a lot of market dynamics that may make this reach some optimum level. Then we imagine a situation where a curve moves as I'm showing, and then it starts to fall. So we see that it rises just like a stone that is thrown. Then it reaches its maximum point, then definitely it has to start sliding. So what we are saying is that in that case, if it's one that has gone and reached its maximum, then we would refer to this point as maxima. This point here, we would refer to this point as maxima. And we see that when it's just turning, after it has reached its maximum and it's just turning, then we realize that what we can say about that point is that it's horizontal, it's actually parallel to the x-axis, in which case the gradient is 0. So that's why we equate the derivatives here, the first derivative and the second derivative. Let me just pick the other pen. Yeah, that's why we, and I should move it like that. Yeah, so basically this illustration, this gives the reason. And another way, we would have had a demand curve that flows like, without using a ruler, let me just try to show you. We would also have a demand curve that flows as such, so that we call this a demand curve, that's D. And then here again, we have a D. So this should look better. That should look better, just a moment. Oh, sorry, I didn't want to remove the whole thing, but okay. So okay, let me leave it as such without having to complicate it. So in this case also, we see that the relationship between price and the demand, the price and quantity, when we are talking about demand, is that when prices are high, you would expect, for instance, when prices are high, we want to say, sorry, let me just pick the right thing. Yeah. So when prices are high, then you see, okay, for instance, we want to consider two positions of price. The first position that I want to consider is this. I want to call it, I want to call this P naught, not necessary. Okay, then just to create a difference, I want to call this P1. But then we see that if prices were to move as such, now, so that we see that it meets that. And then at that point of intersection with the supply curve, we see a straight line. We also see a straight line here. And then here again, we also try to mimic the scenario, and we'll be seeing curve that flows like that. No, I'm not so accurate. I should have used a ruler so that these things are clear. And let me use a ruler. Let me use a ruler to demonstrate this. So first, what I'll do is to do away with this. Wow, that will, yes, good. That has done away with that. I hope that will do away with the latest. Yeah, good. Good. Yeah, so I will call this, just as I'd said, this is, I will call this just as we had labeled it. This is the X, or quantity. I think that's so thick. Let's see what we have. Yeah, let it be there. That's better. That should be better. So that I do away with this. And now let me see how it behaves. So I want to call this, I said, now I want to call this the x-axis. Yeah, that's better. And then this one here is the y-axis, and it's the price. This is the price. And then here, x is the quantity. That is x. So I want to bring a ruler so that I bring in the demand curve, and the demand curve now will behave as follows. Now, imagining an ideal situation, then we would be having curves that look like that. So because I used yellow the other time, I just want to continue using it like that. That's yellow. So that defines that defines my demand curve. So I will call this, sorry, let me just pick it. I will call this, say this is demand. So I call it D. Here is also D because it's a demand curve. And I want to look at different scenarios here, different behaviors of price. So suppose now I have a situation like this. Suppose I have a situation like this. Yeah. So this would be the equilibrium point. I should use the pen so that it flows. So yes. And then lower it a bit for illustration purposes. Lower it a bit, then it becomes yeah. Then yeah, now I want to drop them to find the, I want to drop them so that they find the, so that it finds the x or the quantity. It finds the quantity axis. So I will bring this, I will drop this, I will drop that as such. Where is it? Yeah, I will drop it as this. As, oh no, oh no, oh no, yes, as that, as that, as that. I bring my rule again, drop it again, want to drop it again, I drop it. Yes, now that's it. That's what. Now this one is ugly. This one is ugly. So let's do it again. Looked ugly. Good. We can try it again. So if we try it again, it will be this. And that is so thick. Yeah. So I come here. Okay. Let me bring it. So I want to, okay, now it's properly dropped now. So that's drawn. It's a diagram that I'll be referring to. So that's why I'm taking my time to draw it. I'll be referring to it much often. And so before I quit that point, let me name here. I should name this to be P naught, because now it's the equilibrium. This is now the equilibrium price. So it's P naught. I would call this P1. Then perhaps I'll need up. I'll need another one up. Let me just bring it, because I know later in my explanation, in other areas I will need it, not necessarily this particular question. So this is what it is. Suppose I brought it a little up like that, so that we have this, so that we have this, we have that, we have this, we have that, just like that. And again, we have this, yeah. So it's this again, yeah. So now first we drop this, first we drop that. So 1, 2, yes, that's it. Then yeah, that's, it did that there, and it's also doing it here. So again we have it here. Where is that? Yeah, where it's just closing. We again have it. So sorry, we again have it as such, sorry, yes, yeah. So this is what we have. So that's the diagram. I know having drawn this, I've done much work, and so what is left is just labeling. So probably I will call this P2. I will call this now P2. This is now P2. But then if this is P2, then this corresponding quantity is, I'll call it Q2, because there are two here. This will also be Q. This will also be Q2. So I'll call this QS. Now this is QD because it refers to demand. I'll call it QD. Then this I will call QS. And then I have this. Then this I will call this P P, this is Q naught. This is just Q naught. To mean it is the equilibrium. It's the equilibrium price. It is the equilibrium quantity, and this is the equilibrium price. And then what else do I have here? Here. So this, there is another one here that we missed. This. We missed this. So we bring it. 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 We get it here. So here we get this. Here we get this. We get this. Oh, we get that. Yes, we get that. So this one again now, because it's this, we'll refer to it as QS1. This now will be QS1. I hope we can see the difference, because now we are referring to it, because the price hits the supply. It hits the supply curve. That's why we refer to it as such. So that is that. I've done that much, but I know I'll get to that later. So let's proceed. Let's proceed now. What I have is that now what I needed to show you is how calculus can be used to how and why calculus is used in profit maximization, that we can see in the behavior of curves. So if you were to write your answers, then I would have expected you very quickly to write first the quantity to be optimized as, say, for instance, here we're referring to y is equal to f of x as the function. Then you differentiate it. When you differentiate and equate to 0, you'll be getting one of the optimas. You can test that in the second derivative, and that's just that. So let me look at the second question. I want to look at the second question. Just a moment. Yeah, so now the second question was this: the marginal cost and demand functions for Ujenzi Limited are given as follows. This, that. So we are told that the marginal cost and demand functions for Ujenzi Limited are given as follows. That means that the marginal cost is this is the function, and we are told it's in millions. And then price is x squared minus 24x plus 117. It's also given in millions. Where marginal cost is, MC is the marginal cost function, P is the price of a building constructed, and X is the number of buildings constructed in a year. Now, the total annual fixed costs of the company amount to 39 million. So you are required to get the profit function, that is 2 marks. Then second, you get the selling price per building constructed that will maximize the profit. So this is how we set out to answer that question. Now that we have the question, we need to work it out, and I'll still get my board so that let's see. I want but yeah, I'm setting it up because this is another notebook. Let me just see what I want with it. To format the background, I want dark. That's good for me. So I need to, it's a new page. I need to do this again. So here, and I want to draw it using this. So if I'm using that, yes, that's that. So that's what we have, but I need the pen. Yeah, pen is all right. So pen is okay. So I need to set out to answer that question by first noting that, first we note that the marginal cost function we are given, that is the MC, this is thick, I don't think if I need that. Let me make it better, it's much thicker, I don't need that. So let's see, and reduce it slightly to 3. Yeah, that should be better. That should be better. So MC, the marginal cost, in this case we are given by 2x plus 16, and it's given in million. And price function, the price function is given by P is equal to x squared minus 24x plus 117, and it's also given in millions. So, and again, that's what we have, and we are given the fixed cost. Somewhere along the equation, we are given the fixed cost, which I'll just refer to as FC. It's given to be 39 million. It's 39 million shillings. So X here is the number of buildings per year. So in our case, X is number of buildings per year. So first we should recall that when you are given a total cost function, when you are given, just recall that when you're given a total cost function to be, say, f of x, then we know that the derivative of this cost function, let me not call it TC, let me just call it cost. I just want to call it cost. Let me just call it cost. Let me just call it C. And here again, let me just call it C. So cost, I just want to call it cost, not necessarily total cost. So the derivative with respect to quantity, that is dC dx of f of x, should give us, that is dC, okay, C is actually this. C is actually this. So dC dx is what gives us, this is what gives us what? If you differentiate the cost function, you get the marginal cost. And now that we have the marginal cost, okay, we are doing all this in a bid to define the cost, the profit function. We know that the profit function is defined. Let me just bring it here. If this, sorry, I just enlarged, I zoomed. Let me just make it normal so that we proceed. Yeah, where it was. So let's see, just a moment. Let me remove this. So we are here. 3 is okay. All right. So what I'm saying is that the profit function, we know that is given by this profit function. If we consider profit function to be this, then we know that profit function will be given by the revenue at the output X minus cost at the output X. So the reason why we are doing this is that now if we have the cost function and the revenue function, then we are able to define the profit function. But realize that here we are given the marginal cost. So for us to get the cost function, we would then have to integrate this, because now we are doing the reverse. We would then have to integrate that, because now that means we are doing the reverse. So to get the cost function, because we don't have the cost function, but we have the marginal cost. So we need, but we have seen here without doubt here that we need the cost function. So to get the cost function, we'll have to get it from this. We'll have to get the cost function from this expression here. So I'll set out here and say, the cost function, that is the cost function, is given by the integral. Is given by the integral. I hurried. Sorry. Yeah, let me say. Just a moment. Yeah. So I'm saying the cost function will then be given by the integral of the marginal cost function with respect to quantity. And that will then be that if you come here, it should give you, that is the integral of 2x plus 16 dx. And that that gives us, if you integrate that, that should give you, if you integrate that, it should, integrating this means you simply raise this power by 1 and divide it by the same power. So if I raise already as it is, we have x to power 1, so plus 1, it will be x squared, but that power divides this, so it is x squared, because the 2 divided by 2. So here we just have x squared as the derivative. So I have here x squared plus 16x. Just a minute. Oh no, I have to remove everything, but it's okay. So I'm saying this will be x squared. This will be x squared plus, if you are to integrate this, then you realize that it will now be 16. It will be 16x plus c, the integration constant. It can be c. Let's call it k in this case. We call it k because we have used cost as c. So we call it k plus k as the integration constant. So what we'll do is that then we seek to find out what k is at the point where x is 0, at the turning point that I explained earlier. So I would go ahead to equate to now find the value of k. So if we have fixed cost to be 39 as we had been given, then it means that fixed cost, that is cost that you incur at 0 output. So I'll proceed by saying fixed cost is cost that you incur at 0 output. So what I'll say here is that is okay. What I'll come and say here is that, yeah, I come down here and then I say that at x is equal to 0, we have fixed cost. We have the fixed cost to be 39 million as we had it here. That is the fixed cost, this one, 39 million. So we then want to find the value of k. So we say $39 is equal to, remember x is 0, so here we just have 0 plus 16 times 0, which is just 0, plus k, implying that the value that we want, implying that k is indeed 39. So the constant that we were looking for is 39. So now that we have the constant to be 39, we can then rewrite this equation. Let's see. Yeah, we can then, I'm just trying to see how I move to the next page. Probably it's not one of the options I have here. So I'll rub the next. I'll have to rub from this end. I'll have to rub this. I'll have to rub this. What's it? What's happening? Okay, just a moment. Want to rub. Okay. Just okay. I've drawn an ugly one, but I hope it will help me do it in a flash. It didn't. Okay, let me see this. Should pick an eraser. Go fast. Oh, I rubbed everything. That's okay. It's okay, we can remember. I was not supposed to rub this end, but I did. Okay, that's rubbed. Probably what I need first again is I should be neat. So I have that, already have that. So the next thing is I set out to continue. So just like I found that now I can then write my cost function, the one that we have come up with. I can then write it as x squared, because now I know the constant, plus 16x plus 39. So that's the cost function, and it's in millions. So second, what I do now is to define the revenue function. Now what I need is the revenue function. So the revenue, step 2 is the revenue function, and I will say that the revenue function, that is R of x, should be given by, revenue is given by quantity times price at that level of output, like that. So this should give me x times, we were already given some, we had been given the expression for price. We were given the expression for price as x squared minus 24x plus 117. So we come and bring it there. So it's inside here. I then bring it as x, it is x squared plus x squared, no, it's x squared minus, if there's no plus, it's x squared minus. So I say x squared minus 24x plus 117. So I need to multiply this, and in doing so, I'll be having this by this gives me x cubed minus this times this minus 24 x squared plus 117x plus 117x. That's what I get to be the revenue function. So this is now the revenue. This is the revenue function. That's the revenue function. So with this, then I can then completely specify. My profit function. So I say, therefore, what we had wanted is the profit given by this. So I said, therefore, then there should be a comma. That's ugly. So let me see this. Let me just say this. Yeah. So I say profit function is given by, as I'd said, it's the difference between the revenue function minus the cost function. Sorry, if I have to go with all of it, so be it. So I said it's given by the revenue function minus the cost function. And we know what the revenue function is and what the cost function is. So I'll have to subtract this. I'll have to subtract this from this. So I'll be saying, what I'll then be doing is that I'll be saying x cubed minus 24 x squared plus 117x, the whole of this, yeah, the whole of this, the whole of this, the whole of this, minus x squared plus 16x plus 39. Well, I went up to the end. It's okay, but we can see. So that should give me first, to subtract the like terms. Of course, the first half is x cubed, then minus 24x squared minus x squared is minus 25x squared. Then I have this part here, 117 minus 39. 117 minus 39 should give me, because now, just a moment. No, those are not like terms. Those are not like terms. It will be 117 minus 16. That is 101x. So we say plus 101x plus 101x, because we are dealing with like terms first. 101x, because that is this and this. And then now we have minus 39. It's now minus 39. Minus 39. There's 39 here. There's one here. So this specifies the profit function. So we say this, the whole of this now, this is the profit. This is the profit function as you see it. It's the profit function. This is the profit function as we see it. So that is that. Then the second question. So if that's that is what was required and you did it, then that's right. That's the answer. That's the answer to that part of the question. And if up to there you like the presentation, then you can put the subscribe button, the like button, interact with the video so that help you guys. Part B required us to answer the selling price per building constructed that will maximize profit. So how do we go about that? So again here, just as we were told that it's all about calculus. There's no way you can do this without bringing in calculus. So selling price per building, we'll see that. So that is part B part 2. That should be B part 2. Part 2. Sorry. I do have that. All that. Should have done this. Yes. Now, selling price per building that maximizes profit. First, maximize the profit function with respect to X. And we had seen that the profit function is the profit function we saw is this. This is the profit function as we see it. So if we what we'll do then is to have to the profit function. For us to maximize the profit function again, we'll have to differentiate this. We'll have to differentiate. We get the derivative of the profit function. And how do we do that? This is how we go about it. So we would say the profit function, which is given by this, now would give it a prime with respect to level of output x, will now be given by d dx of this. And that brings us to 3x squared. It is 3x squared, because what happens is that we take this power, pre-multiply it by, we make it the coefficient, then reduce the power by 1. So that gives us that. Then again here we come and say minus this. Now this 2 times 25 gives us 50. So we say minus 50x, because we are reducing the power by 1. And this will just be 101. That will just be 101 as such. That will just be 101. So that's the profit function. That is the derivative. We equate the derivative to 0 for us to get the value of x. At that value of x, then we maximize the profit. So we would then equate this to 0. If you equate this to 0, then you realize that this is a quadratic equation. And a quadratic equation, we can use the quadratic formula, because definitely these values may not allow us to factor. So you recall the formula. It should be x is equal to x is equal to minus b plus or minus b squared minus 4ac minus 4ac. Of course, all of this is under root. All of that is under root. Divide by 2a. So this is the quadratic formula. That's the quadratic formula that should lead you there. And in this case, we see that our a first is the coefficient of our a is the coefficient of x squared. So a, in this case, a will be 3, b will be minus 50, and c is 101. So those are the values you input there. Should you do that successfully, then what you should get is again, I've rubbed the line as well, but no big deal. We are almost there. I think let me just rub the entire board, hoping that notes are already taken and noted. Good. So I pick my pen and move on. Because I'm almost done, I don't need to bring the ruler. So I'll just say that if you work it out, our equation was, what we are dealing with is that 3x squared minus 50x plus 110 is equal to 0. This is the quadratic that we seek to solve. If you solve it using the quadratic formula that had given you, that of x is equals to minus b plus or minus b squared minus 4ac, everything here under root like that, over 2a, you will find that x is approximately, if that is solved numerically, that you should do in your free time, you'll find, because it's quadratic, we expect two values of x, the first being 2.35 buildings, and another one is negative 14.31. So negative 14.31 is not feasible. So we would take 2.3, we take 2.35. So if we take 2.35, then we check the second derivative because we are interested in the maximum profit. So if the first derivative gave us this, then the second derivative of that now should be, we should then have second derivative, that is now the profit function, second derivative now with respect to x, sorry, let me just have this, yes, it's this, will now be given by 6x, because we are here, 2 times 3 gives us 6, reduce that by 1, just 1, minus 50, just minus 50. That's the second derivative. And we see that if we now consider the profit function at the point where we have 2.35 buildings, then you see that we'll be having 6 times 2.35 minus 50. Of course, this is less, this is a minus. So if it's a negative, so if it's a negative, we say that is less than 0. If it's less than 0, then that implies maximum profit. That implies maximum, maximum profit, like that. So up to there, that's what we see. So if that's what we have, then we may need then to the question had asked us to find the selling price per building at that output. So what then we set out to do again is, let me just rub this again to create space. Just want to create space. Let me rub this to create space. Let me rub this to create space. So I've created space because I'm winding up. Yes. So what we then see is that at x is 2.35. Now we want to see, we want to find the selling price, and what we see is that the price was given by the equation. The price as we know it was given by the equation. Price of x was given by the equation P of x is equal to x squared minus 24. This were given in the equation, minus 24x plus 117, plus 117. But now we want it at we want to see that at the output where x is 25 minus root of 322 over 3, and that's exactly what we found to be the value of x if you solve the quadratic equation. So if you solve the quadratic equation, you should find the quadratic equation that we have just referred to, that of let me just write it again so that you see the quadratic, because I rubbed it. We were to solve the quadratic equation. So if you solve this quadratic equation, this one here, 3x squared minus 50x plus 101 is equal to 0, we are saying you should get x to be, just find out that you get x to be this 25. X that you'll find is 25 plus or minus root of 322, root of 322, everything over 3. So we are saying at that point of output where x is this, we now want to define we now want to define the price. So what we'll have is that maximum price that I will define, that optimum price, that we sought to define will then be P X. Actually, I don't need that output. I don't really need to do that. Let me just consider it a P prime. It's just a P star, to mean that now it is optimum. It will be given by this equation, because now we are substituting the value x here. The value x here, we are now substituting in this here, we are putting wherever this x. If you do that, then you are going to find 200 plus 22 root of 322 everything over 9, and it is million. This is million. So and this, if you work it out using a calculator, it's approximately 66.0, sorry, it is 66.09 million shillings per building. So the selling price is about so that's about 66.1 million. So that is the answer as you are expected to give it. So up to there, I've taken long in this presentation, and I beg to stop and meet you in the next presentation. Thank you.